concentrations and temperatures coming into a stirred tank, a perfectly stirred tank, what is the initial steady state conditions? And we're going to solve that in part A in this video here. And so given three streams with the temperatures at different temperatures here, and also differing concentrations and flows as we see here, into a perfectly mixed tank with a cross-sectional area as defined there and a drain hole, we want to go ahead and calculate the liquid height, the temperature, and the concentration of species A if the mixing tank has been operating under these conditions for a long time. And so we're basically trying to figure out how do we set up the differential equations in order to determine what our steady state conditions are going to be. So we're going to go ahead and model that out now. Here's the parameters for flows 1, 2, and 3. And let's go ahead and draw out our tank. And so we've got flow 1 coming in. We've got flow 2 coming in. And flow 3 coming in. And then we have our tank with a fluid height of H. It's perfectly mixed, and we want to determine three different things here, which are how is our height going to be changing with respect to time? How is our concentration of species A going to be changing with respect to time? And then lastly, how is our temperature going to be changing in the tank with respect to time? Because these are the three different flows and concentrations and temperatures and coming in at these different rates. And so how do we actually go ahead and determine how these interact with each other? And so we're going to resolve these one at a time, starting with the height. And so when we're asking the question of how does height change with respect to time, we have to consider the fact that it's the volume of our tank. And how does the volume of our tank change with respect to time? Well, dealing with mass and energy balance, the flow of what's coming in minus the flow of what's going out. That is going to be how our volume is changing over time. Now, the volume that's coming in, the flow rate, not the volume, but the flow rate that's coming in is dealing with the fact that we've got three different flow rates of species A coming in. And then we have our flow rate going out. And our flow rate going out equals, as we've talked about in the previous video series, Bernoulli's equation and potential energy converting to kinetic energy as it leaves. And so that is the area of the hole in which it's escaping multiplied by the square root of 2gh. And then another thing to consider is that when it's our volume, our cross-sectional area, which we're going to call AC, is never actually changing. And so dV dt actually comes to be AC, which remains a constant because the tank in its cross-sectional area is of course staying constant. And so what's changing is the height of our fluid. And so these are the dynamics here. So let's go ahead and actually write this out in its differential equation form. And so if we are concerned with how height changes with respect to time, then that means that we are dealing with 1 over AC multiplied by the summation of from I to 1 and three different flow streams of our flow rate coming in, then minus the flow rate that is leaving. And that is for the first equation with how height changes with respect to time. So now, let's go ahead and, actually let's undo that, make it a little bit cleaner. Okay, so now let's go ahead and deal with how does concentration change with respect to time. Well, here we have, again, asking the question of what's coming in of species A. We would be asking how much species A there is. So the flow rate for each flow coming in with their respective concentrations of A. So that gives us the volume amount of A, which again is going to equal how much A is coming in, so our flow rate coming in, and then how much of A is in each flow, minus what's leaving, multiplied by, we could say CA out, but because this is a perfectly mixed tank, the concentration is going to be CA. And so we'll label it as that. And now, as we did here, our cross-sectional area stays constant. And so the things that are actually changing here is our height and our concentration with respect to time equals 1 over AC multiplied by, actually we could just put this underneath. So let's go ahead and say this. The summation of our flow rates coming in minus what's leaving, and this all divided by AC, the cross-sectional area of the tank. And then now using the product rule, because we've got two dependent variables here in the left-hand side of our equation, this gives us, using the product rule, concentration of A as height changes with respect to time, and then height as concentration changes with respect to time. There, and so I should have actually, oh well. We'll go ahead and rewrite this all again. Should have written the product rule off to the side just so I could have not had to rewrite this whole part. Now, this becomes, if we're curious and we already have our equation for height, and so we're wanting to isolate how concentration changes with respect to time, and so let's go ahead and set that up right here. Hopefully I don't run out of room. I'm gonna have to write nice and small. Actually, let's just do this. Let's just go to the next page. Okay, so now how does concentration change with respect to time? Well, we are carrying over our this right here, concentration times dHdt, and then divided by everything divided by h. And so let's go ahead and write that in now. Equals, okay, so the whole thing is going to be divided by h. Now this part right here, we first have our summation. Our flow rates coming in minus what's going out divided by the cross-sectional area, and then we had brought over concentration and then height and dHdt. There we go. And so this is our equation for how concentration changes with respect to time. Now, lastly is dealing with how does temperature change with respect to time. And so that's our last category here. And so now we have to ask, what is the rate at which energy would be changing in our system? And then asking the question, because we're always asking mass and energy balance, in this case energy balance, with the energy balance, we'd be asking what is the rate at which energy is entering versus the rate at which energy is leaving. And so if we want to consider our factors here, we've got our volume of how much stuff there's going to be, because that's going to impact how much energy is in the system, times the density of our concentration here, the heat capacity, as well as the temperature at which our fluid is at. So that's the rate at which it's going to be changing in our system. So that it's going to be dealing with how much is flowing into our system. So then our flow rates for each of the 3 flows. Now how dense each of those flows are, and then our heat capacity, and then the temperatures, the varying temperatures for each stream coming in minus the stream, the flow leaving, I should say, the density of which that flow is leaving at, the heat capacity, and then the temperature leaving, and again in a perfectly mixed tank, that is just going to be the temperature. And now looking at this, the density and the heat capacity are constant in this case, which allows us to cross out our density and heat capacity across the board. Now, again, we're dealing with the volume, the cross-sectional area stays constant. Looking at our left-hand side of the equation, and so what's left over here is our dH, how height changes, as well as how the temperature changes with respect to time. And then that's going to be over here, 1 over AC multiplied by this whole thing that remains. So we've got QI, actually let's just put this in the denominator. So summation from I to 3 minus the flow of T, all this divided by AC. And then now, again, according to our product rule, which now I'm going to do what I should have done earlier, I'm just going to show what that'll be, what that'll look like over here. So we're going to have, according to the product rule, we have T dH dt plus H dt dt. And so now we're wanting to isolate the final equation, which is how temperature changes with respect to time. And so we're going to move all of this to the right-hand side of our equation. And so that's going to require, let's see here, so our dt, how our temperature changes with respect to time, is going to have the whole right-hand side is going to be multiplied by 1 over h. And so then that leaves us with this right here. So we've got what was currently on the left-hand side of our equation divided by AC minus what was over here, which was how right here. So temperature multiplied by how the height of our fluid is changing with respect to time. And so these are our 3 differential equations that are capturing the mass and energy balance of what's entering, what's leaving our perfectly mixed tank, and how everything, how our height, our concentration, and our temperature are all changing with respect to time. And so now we're going to go ahead and code this out and be able to model how this changes, and then be able to see what our steady state conditions are going to end up being. All right, so now we're going to go ahead and code out what we have just written for our differential equations. And so we're going to start by bringing in our tools that we're going to need. And we're going to eventually plot this out so we can visually see how the dynamics are going to be changing in our process here. Subplots import. So we won't be plotting in this video because we're just trying to determine what our steady state conditions are going to be, but we will in the next video from SciPy. Now this one we are going to be using because we have multiple differential equations that we need to solve simultaneously, and then we are also going to be needing this tool because this is allowing us to use our root solver because we're going to be assessing what are steady state conditions going to be, and this is going to be the tool that we need for that. So bringing those in now. So the next thing is going to be our parameters. And so let's go ahead and bring in our parameters now. So we are dealing with right here. Let's back it up. Oh, so it needs to be refreshed. Okay. So we're dealing with our parameters, which we have our temperature, our concentration of A, and flow in. So let's go ahead and bring those in now. So these are all an array of values that we're dealing with. And so the first one was what? It was 80, 65, and 90 for our 3 streams. 80, 65, and 90. Okay. The next variable, is our concentration of A, and I need to call this initial because this is our initial conditions that we're dealing with here. So that is 0, 1, and 0.5. Okay. Come on. And then our flow in initial, our flows coming in are 0.5, 0.3, and 0.6. Okay. Now, some of the things that we've written out in our equations that we're going to need, well, one is gravity, so we need to put that in. 1, and that's meters per second squared. We are dealing with, we're using our cross-sectional area of the tank, which is meters squared. We're dealing with the cross-sectional area of our hole in which the water is draining, which is 0.1 meters squared. Let's just double check. Yes. All right, and then we are also dealing with, we're looking at this, evaluating this over time, and so we're going to say 100, let's call it 100 seconds. So now we're going to define our right-hand side of our equations, the differential equations that we just wrote out and derived. And so our right-hand side, our independent variable continues to be time, and then we're wanting to assess our dependent variable, which is an array of values, and so we're going to have that as v here. So now in our right-hand side equations, the things that are changing are our flow rates coming in, concentration of A coming in, and our temperature coming in. And so these are the differing parts of our right-hand side equations that we're needing to resolve. And now in our v, we're wanting to unpack this as an array of values, and so height is what's changing, concentration of A is changing, and our temperature is changing. And so we're going to put this into the array of values v that we're trying to assess. So now we need to actually define our functions. And so our Q out, as we recalled, is equal to the flow rate, the area of the hole. The flow rate out is equal to the area of the hole multiplied by 2 times G times H to the 1/2. All right, our dH dt equals, that was our NP sum of our flow rate coming in times, our NP, let's just double check this. We've got, there we go. Okay, how our height changes with respect to time is what's coming in minus what's coming out, all divided by the cross-sectional area. So what's coming in minus what's leaving, all divided by the cross-sectional area. All right, that looks good. Okay, we can get rid of this. There we go. what's coming in minus what's coming out divided by, okay. Now our CA, or concentration of A, is changing. This was, on the next page, we've got the sum of what's coming in minus, so the flow rate of concentration A coming in minus what's leaving divided by the cross-sectional area. Okay, and then, so let's go ahead and get that here. So we've got our MP sum of what's coming in multiplied by our CA coming in, and then this minus what's leaving times, now we said what's leaving the tank, because it's perfectly well mixed, is just concentration A. And so now this whole thing is divided by our cross-sectional area. And then this there we go, minus, what did we say? We said concentration of A times dHdt. Now this whole thing is multiplied by, or in this case we could say divided by H. Okay. Now we have, no, not home, H. Now how does temperature change with respect to time? We said, okay, minus that, flow rate of temperature in, minus T, okay. So a lot of the same steps here. Flow rate coming in multiplied by our temperature coming in minus the flow rate leaving times the temperature that's leaving. Again, that's going to just be T because it's perfectly well mixed, divided by AC, and then this whole thing minus, we said temperature times dHdt, and then this whole thing, this whole expression divided by, I think we said H, right? H, yes. Okay, so there are our 4 functions that we needed to resolve and calculate for each array of values here. So we need to return this as an array of values, so we can actually capture this as each of these things, our height and our concentration and our temperature, are changing with respect to time, capturing this as an array of values, and we are capturing this as our dH dt, concentration over time, and our temperature over time. All right, let's go ahead and calculate that. Okay, great. So now we're going to go ahead and actually use our root solver and determine what our steady state values are over a long period of time. So now that we have all of our functions in place with the right hand side, we're going to use our root solver tool, because what we're trying to ask here is for our dependent variables, our height of the fluid, our concentration of A, and our temperature. We want to determine what are the initial steady state values when this tank has been running and these flow rates have been coming in for a certain period of time. And with steady state, anything that we're evaluating here with our dependent variables are 0 with respect to time. So there's no change with respect to time. And so that's why we're going to use the root solver here, in particular a tool called Lambda, because of determining, we want to determine the steady state values, and later down the road, if we ever want to perform just computational analysis on any change in the system, we're going to want to have a tool that can track that with multiple ODEs here. So our Lambda tool that we're going to use here, and the right hand side of our equations, well, we're going to set an initial time of 0, which is our independent variable, and then our vector of arrays, and then our initial values, initial parameters coming in, I should say. So we've got our concentration and our temperature here. And then we need to provide the root solver just an initial guess. So when it comes to we need to give an initial guess for height and concentration and temperature. And so let's go ahead and determine, we can give a pretty accurate guess for the height at least, because if we ask at steady state, what we know is that Q in is going to equal Q out. In this case, we've got the sum of all the flow rates coming in are going to equal what's leaving. And so we determined that Q out equals the cross-sectional area of the hole times the square root of 2gh, which gives us, so now what we're trying to solve here is for h. And so that would have us take the sum here, divide by cross-sectional area of the hole, divided by, then square root this, and then divide that by 2g equals h. So that's what we're going to go ahead and code here for h as our initial guess for the root solver. So let's go ahead and say NP array. So the height first, we're saying NP sum of Q in naught. And what did we say? We said that that needs to be divided by cross-sectional area of the hole. And then this whole thing is getting squared. And then divided by 2 and divided by g. Okay. Here we go. Divided by 2, divided by g. All right, now that's for our height. Now our concentration. Well, let's see, we've got 0, 1, and 0.5. So let's just hit it down the middle with 0.5 for concentration. And then for temperature, we've got 80, 65, and 90. Let's say 75. Okay. Now let's go ahead and, do we need to close any brackets? I think we're good. Okay, it said it converged, so let's call this solution. And let's see what our initial steady state parameters are. So here it's telling us that our steady state parameters, so our first one that we were solving for is height, and so the height of the fluid at steady state is going to be 9.99, almost 10 meters high in the tank. Our flow rate, our concentration of A at steady state is going to be 0.43, and then our temperature in the tank is going to be 81 degrees roughly Celsius. And so these are our steady state parameters in our mixed tank, where we have multiple flows with different concentrations, different flow rates, and different temperatures. And this is what the steady state parameters are going to be in the tank. And then now we're going to move on to part B, in which we evaluate a change in the parameters coming in and how the we're going to perform computational analysis to see how that changes our system and the process that happens. Thank you.